notice, like I said, these are our common reagents, and the first thing we want you to notice is that these are symmetrical, like you just pointed out. That is correct, because you have the same atom on each side of the bond. How does that change with those bottom two? These are asymmetrical. Okay? This looks like it's symmetrical, but it breaks apart in that manner, because you don't have the same thing on both sides. That's the very first thing you're going to want to identify. What type of reagent do we have? Is it a symmetrical or asymmetrical reagent? Okay. So then the next thing we want you to identify is your parent chain. Is that symmetrical or asymmetrical? Okay. And okay, now when you look at those two parent chains, one of them is 2-pentene, the other one is hexene, I think. 1, 2, yep, hexene. Do you think, are those both symmetrical, are they both asymmetrical, or is there one of each? That's the next thing you're going to want to identify. That's correct, okay? Now, the trap that you can possibly fall into, okay, is now that you've said that there's one of each, can you recognize which one's which? This one's symmetrical, and that one's asymmetrical. That's right. Now, we don't go by this having 3 carbons on one side and 2 on the other saying that's asymmetrical, okay? The only reason that we say that this is asymmetrical is because it's on the end. This is anywhere other than the end, okay? And we've seen something like this before. With our organic families, okay? The second one down is a ketone. The top one is an aldehyde. What we use or say is that when that double bonded oxygen is on the end, it's an aldehyde. If it's anywhere other than the end, it's a ketone then. You could say even if it's over here. It doesn't matter. It's not on the end, so it makes it a ketone. So we use that same type of logic here. If it's on the end, it's asymmetrical. If it's anywhere other than the end, it's asymmetrical. Okay? Now, just because we've got asymmetrical reagents doesn't mean we're always going to get 2 products. Or excuse me, you're going to get 2 products, but you might not have to list them as major and minor. Okay? And one of the aspects that we said you can do, you can talk to one of your classmates, or what other resource do you have besides coming in here? There's also a textbook that you can use that has the same information in here, okay? Because some of these skills, you're going to have, whether it's this or learning in your next step in your academic career, when you decide that I need help, you need to go out and seek that, okay? We can't teach you that, all right? And we're trying to push us down the tracks as far as possible, okay? And it's just one of these things we're trying to recognize this. And what I mean, if we add which one of those would give you a major and a minor product, do you think? You're going to get two products here, you're going to get two products here. But which one? This one has a major and a minor product. Okay? If it's symmetrical, you don't have to have a major and a minor. That is correct with this one here. Okay? And you do get two products, but they just form in equal amounts. Okay? Because remember, where is bonding available? Well, right here and right here. When that double bond breaks, it happens very easily. Okay? You can't follow which rule for this. That's why you don't have a major and a minor. It starts with the letter M. Okay? Markov-Nikov's rule. It's something that we talked about in class. Okay? And what we see happening then, well, we'll do this bottom one since we said Markov-Nikov's rule. When this splits, what is that hydrogen looking for? Okay. Do we have our notes that we were taking? What is Markov-Nikov's rule? My fear is I don't want to keep going through and just showing you how to do, well, showing you that's fine, but just doing the work for you. Then we just don't learn. What does Markov-Nikov's rule say? In a matter of terms, yes. This hydrogen is looking for the carbon that already has the most hydrogens present. In this case, there's only bonds that can take place here and here. So when that happens, which one of these two carbons has more hydrogens? This one's got 2, this one's got 1. So therefore, we would see okay, if we want the major product, the major one, where does that iodine go? Which one of these two spots? The second one, okay? Then that hydrogen goes on this first one. This is your major product, okay? Then you also have this minor one. Where if it's not on the second one, it's just on the end. Okay? Because what we see with this top one okay, there's bonding that can take place here and here. But notice, Markov-Nikov's rule doesn't apply here because each one of these already has one. Okay? And neither one of them have 2. They each have the same amount. So we'll just go ahead and put that hydrogen here. This iodine here, that's 50% of it. And then we can also put that iodine down here and that hydrogen up there. That makes up the other half of it. Okay? For this one here, okay? Okay, so part of this is naming, part of this is reactions tomorrow, all right? Yay, we can't wait. We got to have something to show your parents at parent-teacher conferences, right? We get to show them how smart we are. This How many times have we said you've got to wrap your head around this? This is not easy stuff, okay? And I applaud you for making the commitment for taking this class, because it is difficult. No one's going to deny that. Anything else? Okay. But is there a type of symmetrical reagent that will not react? Yes, there is. And that is what? Hydrogen. Okay, that has to have a catalyst. Okay. For some reason, hydrogen just needs to have that extra boost where, whether it's a halogen here or the asymmetrical reagent that we see, like for instance, if this is just fluorine, F2 or 2 fluorines, okay, that will react even without a catalyst here. But if we see this, then yeah, you need to have a metal catalyst here or something, some form of heat maybe, or something like that. Yep. And when you receive the paper, yes, it will be written correctly, so maybe it will just look like that. And then you would say, erase all of this now and say, no reaction. Okay? All right. And sometimes what happens, you're always going to be thrown curveballs in life. I don't know if you want to look at it that way, or maybe a bad call in volleyball or football, basketball, any one of those. It's something that you're always going to have to deal with and have to find a way to get past that. Is it easy? No. No one ever said it was. It's just something that it's all part of growing up and maturing and growing older and being self-sufficient. Anything else? Just as long as there's no combustion reactions on there from last year. But do keep in mind, any chemistry class that you take in college, even if it's an organic, you may have to review some of those general chemistry concepts that you had taken here, and hopefully, if we've done our job, have adequately prepared you for those. Otherwise, if there's nothing else, I'll leave you be and ready to get, or how do I want to say this? Prepare for the rest of the day. Left side, we're good. Middle, right side. We'll just say it just so he shuts up. All right, very good. We'll catch up to you. I guess on Tuesday will be the next time that we see you.